Dear students, in the previous lecture I have given introduction to exponential smoothing. In this lecture I am going to explain the working of exponential smoothing model with a sample problem. I am also going to explain how to use spreadsheet for exponential smoothing. After that I am going to discuss about an interesting and powerful forecasting technique called regression model. In this lecture I will explain how to build a regression model. In the next lecture I will explain how to use this model for the forecasting. So, the agenda for this lecture is exponential smoothing problems and linear trend forecasting using regression model. First we will start with exponential smoothing. Despite the fact that exponential smoothing provides a forecast that is a weighted average of all past observations, all past data do not need to be retained to compute the forecast for the next period. For example, here look at the formula. If it is, suppose if I want to forecast for t equal to 1, for example y2. So, what I need is I need alpha of y1 plus 1 minus alpha of y1 hat. That means, for forecasting for the next period I need the previous period actual value with alpha weightage plus the previous period forecasted value with 1 minus alpha weightage. In fact, the above equation shows that once the value of the smoothing constant alpha is selected, only two pieces of information are needed to compute the forecast for period 2 plus 1. What are the two pieces of information? Yt, the actual value of time series in period t, and yt hat, the forecast for period t. To illustrate the exponential smoothing approach for forecasting, let us again consider the gasoline sales time series in table 1 and figure 2. The reference for this problem is from Anderson et al. As indicated previously, to initialize the calculations, we set exponential smoothing forecast for period 2 equal to the actual value of time series in period 1. This was the given data. For this data set we are going to find the exponential smoothing. Thus, with y1 equal to 17 and y2 hat also taken as 17 to initiate the computation. Here y2 hat is this value. Referring to the time series data in the given table, we find an actual time series value in period 2, that is y2 is 21, but the forecasted value is 17, that is the y1 actual value. Continuing with the exponential smoothing computation, using a smoothing constant of alpha equal to 0.2, we obtain the following forecast for period 3. So, y3 hat equal to 0.y2 plus 1 minus alpha, that is 0.8 y2 hat. So, what is the y2? y2 value is 21 plus 0.8, y2 hat is 17. So, the forecasted value for the period 3 is 17 point, that is this value 17.8. Once the actual time series value in period 3 is 19 is known, we can generate a forecast for period 4. So, we have to extend that same equations for y4 0.2 y3 plus 0.8, that is 1 minus alpha y3 hat. What is y3 actual value? It is 19. What is y3 hat? The forecasted value for period 3, that is 17.8. So, this 17.8. So, we have got the forecasted value for the fourth period, that is 18.04. Continuing the exponential smoothing calculations, we obtain the weekly forecast value as shown in the table. Note that we have not shown exponential smoothing forecast or a forecast error for week 1. Continuing with the exponential smoothing calculations, we obtain the weekly forecast value shown in a table, that is in the next slide I will show you. This is the complete exponential smoothing where alpha equal to 0.2. Note that we have not shown an exponential smoothing forecast or a forecast error for week 1 because no forecast was made. We used actual sales for week 1 as the forecasted sales for week 2 to initialize the exponential smoothing process. So, this is the point that we are not having any error here because we have taken the actual values of the period 1 as the forecasted value. So, what we have done here, we found the forecast error, then absolute value of forecast error, then we found the squared error, then percentage error, then absolute value of percentage error. At the bottom of this table we have found the sum of this forecast error that will be used for calculating some of the measures of accuracy for the forecasting. The actual and forecast gasoline time series with smoothing constant alpha equal to 0.2. So, the actual value is in blue in color, the forecasted value is red in color. You see that it has got leveled. For week 12 we have y12 equal to 22 and y12 hat is 18 point, that is forecasted value for week 12 is 18.48. We can use this information to generate a forecast for week 13. So, week 13 we can generate the forecasted value. So, for week 13 there are two informations required, week 12 actual value and week 12 forecasted value. So, week 12 the actual value is 22 and the forecasted value is 18.48. When you substitute there we are getting 19.18. Thus, the exponential smoothing forecast of the amount sold in week 13 is 19.18 or in actual units it is 19,180 gallons of gasoline. With this forecast the firm can make plans and decision accordingly. The figure shows the time series plot of actual and forecast time series values. Note that in particular how the forecast smooth out the irregular or random fluctuation in the time series. Initially the blue color says that there are some irregular pattern. By using exponential smoothing that the irregulars are removed. Now, we talk about the accuracy of this exponential smoothing. In the preceding exponential smoothing calculations, we used a smoothing constant of alpha equal to 0.2. Although any value of alpha between 0 and 1 is acceptable, some values will yield more accurate forecast than others. Insight into choosing a good value for a alpha can be obtained by rewriting the basic exponential smoothing model as follows. We know the forecasted value for yt plus 1 is equal to alpha into yt plus 1 minus alpha into yt hat. If you expand this, so alpha into yt plus yt hat minus alpha into yt hat. So, yt plus 1 hat equal to yt hat plus alpha can be is common. So, it can be taken out. So, yt minus actual minus forecasted value, that is nothing but your yt plus 1 is nothing but the previous year forecast plus alpha into error term. Thus, the new forecast yt plus 1 is equal to the previous forecast yt hat plus an adjustment which is smoothing constant alpha times the most recent forecast error yt equal to yt minus yt hat. That is, the forecast in period t plus 1 is obtained by adjusting the forecast in period t by alpha fraction of the forecast error from period t. If the time series contains substantial random variability, a small value of the smoothing constant is preferred. The reason for this is that if much of the forecast error is due to random variability, we do not want to overreact and adjust the forecast too quickly. For a time series with relatively little random variability, a forecast error is more likely to represent a real change in the level of the series. Thus, the larger values of the smoothing constant provides an advantage of quickly adjusting the forecast to changes in the time series. So, this allows the forecast to react more quickly to changing conditions. The previous slide also I have explained how the value of alpha will affect the result. For example, when alpha equal to 0.2, our value was like this. Even say this is year 1, 2, 3 and even the 10th year data also got some values. Suppose the alpha equal to 0.7. So, what will happen, that initial value is getting some values, the value for year 10, year 11 almost is becoming 0. The criterion we will use to determine a desirable value for the smoothing constant alpha is the same as the criterion we proposed for determining the order or the number of periods of data to include in the moving average calculations. The order is k. That is, we choose the value of alpha that minimizes the mean squared error. A summary of mean squared error calculation for exponential smoothing forecast of gasoline sales with alpha equal to 0.2 is shown already in the table that I have already explained. Note that there is a one less squared error term than the number of time periods. This is because we had no past values with which to make the forecast error for period 1. So, we have 12 years data, but we have divided by 11 because for the first year we do not have any error. This value of the sum of squared forecast error is 98.80. So, when you divide this 98.80 by 11, we are getting 8.98. Would a different value of alpha provide better result in terms of lower mean square error value? Trial and error is often used to determine if a different smoothing constant alpha can provide more accurate forecast, but we can avoid trial and error and determine the value of alpha that minimizes mean square error through the use of nonlinear optimization. This nonlinear optimization already I have explained in my previous lectures. So, that chapter is under nonlinear optimization problems. That lecture you can refer how to get the right value of alpha that will minimize the squared error. So, here minimizing squared error is a nonlinear objective functions. There what value of alpha will minimize the mean squared error. So, that alpha is the most appropriate. Now, I am going to explain how to use spreadsheet for doing exponential smoothing forecasting. So, I have taken 12 weeks data and I have the sales value. So, you see that C3, look at the 17.8, that is C3, that is our year C3. Look at the formula there, alpha into B3, that is 21 plus 1 minus alpha into C3. So, to know that actually in Excel, so in the C column I have used alpha into yt plus 1 minus alpha into yt. So, I have got a exponential smoothing values for the C column. Then I found the forecast error in the D column. Then I found the absolute value of forecast error. So, what equations I have used, what functions I have used in Excel, there is a absolute function value. Then I found the squared error, actual minus predicted value. Then I found the percentage of error. The percentage of error is error divided by the actual value. Then I found absolute value of percentage error. At the end I have summed all the totals. So, from that I have found the mean absolute error, then mean squared error and mean absolute percentage error. This is one way to do Excel, but in Excel there is a built-in function is there. now I am going to explain how to use a spreadsheet for exponential smoothing. So, go to data analysis, choose exponential smoothing. Here we have to select input range, then here damping factor you have to take the 1 minus alpha. So, our alpha value is 0.2. So, the damping factor is 0.8, there is a labels. So, I have to select the output range. You see that I have selected output range not for the week 1, week 2 onwards, week 2 to 12 weeks. So, when I press OK, look at the values in C and values in I, both are same. So, we can use Excel for exponential smoothing, and we have got corresponding the plot also. So, the orange color shows the forecasted value, the blue line shows the actual value. Dear students, next we are going to discuss about trend forecasting. This trend forecasting, we know what is a trend. What is a trend? Trend will be like this. So, what we are going to do for this? We are going to do a regression analysis. First of all, what is the difference between, in terms of application, correlation and regression? A scatter plot or scatter diagram can be used to show the relationship between two numerical values. Correlation analysis used to measure strength of association, that is linear relationship between two variables. Correlation is only concerned with strength of the relationship. No causal effect is implied with the correlation. But in regression, we can say which is independent and which is dependent variable. But in correlation, we will not say which is dependent variable, which is independent variable. That is a major difference between correlation and regression analysis. Now, we will discuss about the regression analysis. Regression analysis used to predict the value of dependent variable based on the value of at least one independent variable. It explains the impact of changes in independent variable on the dependent variable. Suppose if I write this way, y equal to b0 plus b1x, this is an example of regression analysis. What says that it is predicting, here y is the dependent variable, x is the independent variable. What is dependent variable? The variable you wish to explain. What is independent variable? The variable used to explain the dependent variable. First, we will discuss about a simple linear regression model where we are going to use only one independent variable. So, in simple regression analysis, only one independent variable will be used, and the relationship between x and y is described by a linear function. So, changes in y are related to changes in the x. So, if I used only one independent variable, okay, this way, this is an example of simple linear regression model. We may have different types of relationship. So, this one is following linear relationship, positive linear relationship. X increases, y also increases. The bottom one, if x increases, y decreases. On the right hand side, you are able to see the curvilinear relationships. But in this regression, we are going to consider only the linear relationship models. And types of relationship, whether it is a strong relationship or weak relationship. Look at this picture on the left hand side. Here all the actual points, that blue dots represent actual points, these are packed together. Okay. So, it is having a strong relationship. The variance, the dispersion is very less. But look at the right hand side, the variation is more. So, that means it is the weak relationships. The top one, weak relationships with positive slope, the bottom one, weak relationship with the negative slope. Sometime there may not be relationship at all. See the top one x and y, there is no connection. It is the level type of data, that is whatever may be the value of x, the value of y is somewhat similar to constant. So, here we can say, for example, here x and y are independent. That means what? X, the value of y is not affected by the value of x. Now, the linear regression model, you should be very careful. Sometime I say linear regression model, sometime I say linear regression equation. If we say model, that represents the population. So, yi dependent variable, this one, equal to beta 0 population y intercept plus beta 1 population slope coefficient xi independent variable plus random error term. So, this component is a linear component, this is error component. These equations for expressing the regression model for the population, because we have included a error term here. Not only that, all capital letters represents the regression model for the populations beta 0, beta 1. In case if I write B0 plus B1, this represents the regression equations for the sample. That is the difference. There won't be any error term, that I will explain why. Now, look at the linear regression model. The beta 0 represents the y intercept. This epsilon I represents the error term. That is, what is the error term? Difference between actual value and predicted value. And this red line shows the regression model, and the slope is this beta 1. Now, you see, now I am saying linear regression equations, and when I say equations, look at the equation here, that all are in small letters beta 0, sorry, B0 plus B1x, and see this, there is no error term here. If there is no error term, we call it as regression equation for the sample. Why there is no error term? That the way we have got the value of B0, B1, it takes care that error is minimized. So, what will happen when you say the expected value, this y hat is nothing but the expected value of for y equal to, we can write expected value of y, that is the mean of y value, that is very important. Estimated or predicted y value of observation I, it is not actual value. So, what I mean here not actual value is, suppose the data is like this, data is like this. The equation which I am drawing is not the actual value, it is the mean value or the expected value. So, what will happen? Any error term, the expected value of error term is equal to 0. What is the meaning? There will be a positive error and negative error. If you add that, the expected value of error will become 0. That is why there is no error term here. Here B0 and B1 are obtained by finding the values of B0 and B1 that minimize the sum of the squared differences between y and y hat. The way, the logic behind how we are finding this slope and the y intercept is that the sum of the square of the error has to be minimized. For example, if I have data like this, there are different ways. I can draw a regression equation like this, I can draw a regression equation like this, or I can draw a regression equation like this also. But how do you know the best regression equation? That means for each regression type, we have to find out the error, we have to square the error, then we have to sum the error. For example, the first one, the sum of the squared error is 25. For second one, the sum of the squared error is say 20. For third one, the sum of the squared error is say 30. So, we can say this second one, the middle one line is the best equation, because that has minimized sum of the square of the error. That is the concept of your least square method. yi minus y hat we know b0 plus b1x whole square, because why I am squaring the error, so that it will become positive. Not only become positive, if there are more deviation, when you square it, it will become higher values. For example, if the deviation is 5, when you square it, it will become 25. If the deviation is 0.5, when you square it, it will become 0.25. That is the reason we are squaring the error. If you are not squaring, the sum of the error will become 0. The purpose of squaring is to provide higher penalty for higher deviations and lesser penalty for lesser deviation. That is the beauty of this squared transformation. B0 is the estimated mean value of y when the value of x is 0. B1 is the estimated change in the mean value of y for every 1 unit change in x. Now, to construct a regression equation, we need two things. One is B0, another one is B1. Suppose if I write as y hat equal to B0 plus B1 x. Suppose in regression equation is like this. So, this length is B0, this slope is B1. There is a detailed calculus is there how we are getting B1 and B0, but I will tell you the logic behind this B1. So, the B1 is nothing but covariance between x comma y divided by variance of x. What is the covariance? Covariance is sigma of x minus x bar, y minus y bar upon n minus 1. What is the variance of x? Sigma of x minus x bar whole square divided by n minus 1. So, this n minus 1, this n minus 1 get cancelled. So, what we are getting? Sigma of x minus x bar into y minus y bar upon your sigma of x minus x bar whole square. Once we know the slope, next we have to find out the y-intercept. The another logic is, if you want to draw a best regression line, it has to pass through, this is the x axis, this is y axis. If you want to draw a best line, that has to pass through the value of x, that is x bar, not value, the mean value of x, x bar, and the mean value of y, y bar. So, one of the point should be x bar comma y bar, then only we can say the line which I have drawn is the best line. We know that y cap equal to B0 plus beta B1x. Suppose this line is passing through x bar comma y bar, what will happen this? So, this will become y bar equal to B0 plus B1 x bar. Already we know the B1 value, then we can substitute. From this we can find out B0, that is B0 is y-intercept. So, B0 is y bar minus B1x, B1x bar. So, this is the formula for your slope and y-intercept, but in our class we are going to use directly the spreadsheet, but you should know what is the logic behind this slope and y-intercept. So, I have taken one sample problem. A real estate agent wishes to examine the relationship between selling price of a home and its size, that is measured in square feet. Here the selling price of the home is taken as your dependent variable and its size is taken as independent variable. A random sample of 10 houses is selected. So, the dependent variable is house price and the independent variable x is square feet. This is an x value, this is an y value. I am going to use spreadsheet for this data, how to do the regression analysis. before doing the regression analysis, the first step is you have to plot the scatter plot. The purpose of scatter plot is to get a rough idea is there is relationship between x and y. You see that you can see a kind of a trend. That means we can plot a regression model. Suppose this scatter plot shows that there is no relationship at all, then there is no point in doing the regression analysis. So, the first step for drawing a regression equation is first you have to draw a scatter plot to confirm that there is a relation between x and y. Dear students, now I am going to explain how to do the regression analysis with the spreadsheet. So, you have to click data. I have the data here. So, the data, I got a data analysis tab. Sometime some students they may not have this data analysis tab. For that people what you have to do, this is an add-in in Excel. So, you have to go to file, then you have to go to options, then you have to click on add-in, So, you see that here the analysis toolpack is activated. If it is not there, it will be under inactive application add-ins. So, you have to select that, you have to press go, you will get a, you have to press go. You see that already I checked it, because in this system already I have installed, is already checked it. When you press OK in your computer also it will be enabled, then you can, once you press the data tab, you will get the data analysis tab also. So, go to data analysis, so go to regression, so click OK. You see that first you have to select y, dependent variable. So, select the dependent variable including labels. Next you select the input range. Here we have only one input, so I am selecting only one. If there are more than one input, you have to select all the inputs at a time. Then click the labels. There are other components there, residuals, standard residuals, residual plots, normal probability plots, that I will explain in the next lecture, but at present we are going to predict, we are going to construct only a regression model. So, press OK. Now, we got the y-intercept as 98.24 and the slope is 0.109. Yeah, you see the y-intercept 98.24 and the slope is 0.104. There are other values there like r, r square, adjusted r square, standard error, and we have got the ANOVA table also. And there are other ways to interpret, for example, t value is there, p value is there, lower 95% limit is there, upper percentage limit, that I will explain in the next class, but at present we are looking at only the intercept 98.24 and the slope 0.109. So, how we can write the regression equation? For example, so we can write the regression equation y equal to 98.24 plus 0.109 x. So, this is our regression equation. Now, I will go back to the presentation. I will explain pictorially what is this 98.24. First, you have done the scatter plot, look at the intercept. So, this value is your y-intercept and the slope is 0.10977. So, what is the dependent variable? So, house price equal to 98.24 plus 0.109 square feet. There is a small rounding error there. So, how to interpret the y-intercept? B0 is the estimated mean value of y. when the value of x equal to 0. If there is no independent variable, the B0 is an approximate value of our y value. That is, if x equal to 0 is in the range of observed x value, here B0 is the mean of all y values. Because the square footage of the house cannot be 0, then y intercept has no practical applications. So, the y intercept sometime we cannot interpret it, because in this context, so when you substitute x equal to 0, that means there is no square feet, we are getting the price is 98.24, but how it is possible? If there is no square feet at all, how can 98.24, how can a house price 98.24? So, there is no meaning to interpret the y intercept, but we are going to interpret the coefficient of square feet, that is x. So, B1 measures the mean change in the average value of y. Remember, the house price is the average value, it is not the exact value. So, average value of y as a result of 1 unit change in x. So, if the square feet is increased by 1 unit, what is the corresponding change in the house price? That is the meaning of slope. So, here B1 is equal to 0.10977 tells us that the mean value of house is increased by 0.10977. In actual term, it is $109.77 on average for each additional 1 square foot of size. Dear student, in this lecture I have explained how to use spreadsheet for exponential smoothing models for the sample problem. I have also explained the fundamental concepts of building a regression model for forecasting. In the next lecture, I will discuss how to use the regression model for prediction. Thank you.